Hey Science 20s, yesterday you would have looked at some slope, and that is taking the rise over the run. It's a really small part of our curriculum, so we're going to move on to a much bigger part, and we're going to work over this the next couple days, and that's acceleration. Now, acceleration is non-uniform motion. It's the change in velocity over the change in time. What does that mean? Acceleration is how much faster or how much slower you're going over time. It's like flooring it when you're in a car or slowing down to a red light. You're changing your speed over time. And the formula looks like this. Acceleration is equal to Vf minus Vi over delta t. So this is our first much more trickier formula. Vf is velocity final, and Vi is velocity initial. You probably know that delta t is time. Now, both velocities need to be in meters per second, and the time needs to be in meters per second. So we're going to have to do some converting if our units don't match up. Okay, so I think we should just jump right into a couple problems and try them out. Okay, here's the first problem. After leaving a red light, you accelerate to 60 kilometers an hour in about 6 seconds. What is your average acceleration? All right, first step. Let's write down the formula that we need. Acceleration is change in velocity, Vf minus Vi over time. Now, our final velocity is 60 kilometers an hour. That's what we got to. If we were at a red light, what do you think our velocity initial was? If you said 0, you're right. We went from 0 to 60. And the delta t is 6 seconds. Okay, so we have to do a little bit of conversion before we can throw our numbers in there. We have to convert 60 kilometers per hour into meters per second. Okay, so let's set up our ratio. In 1 kilometer, there's 100 meters. And in 1 hour, there's 3,600 seconds. That gets rid of kilometers, and that gets rid of hours. So 60 kilometers per hour, when I throw that into my calculator, gives me a rough 16.7 meters per second. Okay? And that is our velocity final. Okay, so now we can put our numbers in there. Our velocity final is 16.7 meters per second. Our velocity initial is 0 because we were at a stop. And our time is 6 seconds. So when I divide that out, I get around 2.78. And maybe we should just round that to 2.8. And our units are meters per second squared because we're dividing time by itself again. So this is a big deal. Our units for acceleration is meters per second squared. All right. Now, this is a vector. I'm going to say this is positive acceleration because I'm getting faster over time. And when I subtract these, I do wind up with a positive number. Okay. Let's try another one. A little bit simple. All right, so we've got the Bugatti Veyron, however you call that. It used to be one of the quickest cars in the world. So it goes from 0 to 100 in 2.4 seconds. What's the acceleration? All right, acceleration is Vf minus Vi over change in time. Now, let's change our velocity final right away to meters per second, right? We've got 100 kilometers per hour. Let's just change that quick. Kilometers on the bottom, 1,000 meters on top. hours on top, 3,600 seconds on the bottom. Kilometers cancel, hours cancel, right? So it's the same conversion as above. So 100 times 1,000 divided by 3,600 gives me, we'll go 27.8 meters per second. Okay. Now we went from rest, so the car's like not moving at all to start with, 0. So maybe this is some kind of drag race, and our time is 2.4 seconds. So let's throw the numbers in there. Our final velocity of the Bugatti is 27.8 meters per second. We have 0 meters per second because we started initially at not moving, over 2.4 seconds. So when I divide that out, I get around 11.6. And what's our unit for acceleration? Meters per second squared. Now, were we moving faster over time? The answer is yes. So we have positive acceleration. Okay. Let's try another one. This one's a little bit trickier. Okay, we've got terminal velocity is about 100 meters per second. So terminal velocity is how fast you can possibly be moving as you're falling. So you don't get to go much faster than that on Earth because you reach a speed where the wind and the air around you is slowing you down. You can't go any much faster than that. Okay? So, and acceleration due to gravity is how fast gravity accelerates you back towards the ground. So let's just set up our formula. Acceleration is equal to VF minus VI over change in time. Okay? Now, what's different about this is it gives us the acceleration. All right? Now, our final velocity is 100 meters per second. Before you started to fall, what do you think your speed was? 0. So we need to rearrange for the time variable. And if you remember, if you have something on the bottom, you can just do a little switchy thing to get time by itself. So time goes right there, and acceleration goes on the bottom. See how I switched time and acceleration around? Our velocity final is 100 meters per second. Our velocity initial is 0 meters per second. And our acceleration is 9.81 meters per second squared. Okay, so all I have to do is divide that out. So hopefully you can refer back to this video and some of the problems you'll do today. I get 10.2 seconds. Okay, that's good for today. You guys are going to be working on a worksheet that will be due when we get back from spring break. So you can start a bit of it today, and we're going to be working on more acceleration tomorrow, but it's going to be chunked, just that we're not too overwhelmed with this. It's kind of a tough concept. So that's the end of this video, and if you read the plan, there will be a few questions that I'd like you to do, maybe today, like try a couple, and then you can work on the rest tomorrow, and if you don't get it done, you have the rest of spring break to kind of whittle away at it. But that's the lesson for today.